Hey guys, Mr. Smith here in the dungeon, and today we are talking about transformations. You guys were introduced to transformations way back in your grade 10 course when you transformed quadratic functions. In your grade 11 course, you revisited transformations, you added a couple more to your repertoire, and you transformed more functions, like you transformed the sine function you learned about, exponential functions, but you transform more functions. In this lesson, we're kind of reviewing those transformations and we're applying them to basic power functions. So let's get started. First, I have you guys doing some. First of all, why is it useful? It's useful for modeling. So here, for example, is an architectural design, and this is a pattern in the crown molding. And if you think about it, this pattern here could be modeled by, well, for example, my tablet pen stopped working. Where'd you go, tablet? There we go. Each one of these guys can be thought of as like, well, there's a cubic function with that in behavior, or you can think of it as, and the other side of that could be like a cubic function that has that opposite end behavior with like a leading coefficient of -1. Or you could view each of these sections maybe as like possibly a quartic function and a quartic function with a negative leading coefficient. And each of these patterns is kind of like shifted over and kind of repeating. And the big idea is you can model lots of things with, well, not just power functions, but any functions. In this particular lesson, though, we're more concerned with, can we apply transformations to power functions? So we're going to review the roles of A, K, D, and C, those parameters you used in your grade 11 course when describing transformations. But we're going to only look at polynomial functions of this form. So essentially, we're just transforming your basic power functions. All right, let's get into it. So just as a bit of a refresher, I've got some groups of functions for you guys to graph, and my intention is that you guys load up Desmos or the graphing program of your choice and have a look at what these three graphs look like. And then for each of these groups of graphs, I'm asking you if you can describe the effect of, in this case, what adding or subtracting a number after some base function is. So for each one of these, you can pause the video, graph the functions, describe the rule on your own, and then we'll come back together, talk about what the three graphs look like, and then describe the effect together. So I'll just assume you've tried it and you're ready to go. I've got these loaded up in Desmos already. And here's our first group. So here's the first guy, the basic quartic function, y equals x to the power 4. We can see x to the power 4 plus 2 has the same general shape. It's just shifted up 2 units. And x to the 4 minus 3 is the same basic shape, but shifted down 3 units. And so I'm just going to transfer a very rough sketch to my node here. So basic quartic function. And then we saw x4 plus 2 is just shifted up. Same general shape. X to the power 4 minus 3 is shifted down. And if you said something like horizontal shift or horizontal translation, that's great. The effect of C, adding a number after the base function or subtracting, we describe it as a vertical shift or vertical translation of the base function. So if C is greater than 0, so if this number on the end, like in our second guy here, if it's positive, the graph shifts up by the number indicated. And then if it's negative, it shifts down by the number indicated. So it goes down by 3 units for the last example. So that should sound familiar from your earlier courses. But we're going to review all the types of transformations that we should be aware of at this point. So let's continue. In the next group, the base function you're going to work with is the quintic function, y equals x to the power 5. And then you're doing 2 transformations of that. So pause the video, try those out, and unpause when you're ready. All right, I'm going to assume you've tried that. I'm going to head over to Desmos. And here we go. And so here's our basic quintic function, that end behavior we're familiar with, point of symmetry about 0, 0. So in the previous one, when we added 2 on the end of x to the power 4, it shifted up 2 units, kind of what we expect. Now, possibly common sense would indicate to you that if we're adding 2 off the x, then this graph might get shifted not up or down, but possibly left or right. And since it's positive 2, maybe it'll shift to the right 2 units. But actually, what you guys have discovered in your grade 10 and 11 courses is that adding a positive number off of the x actually shifts it to the left. It's kind of counterintuitive that way. And you would have talked about the y's of that in your grade 10 or 11 course. And x minus 4 to the power 5 actually shifts it to the right 5 units. So getting those onto our lesson sheets, rough sketch of the quintic function. And then this gets shifted over 2 units, has the same shape. And then this guy was shifted over 4 units, has the same shape. Okay, but the moral of the story is when you add or subtract a number off of the x in some base function, what you get is a horizontal shift or horizontal translation. Now, things are a bit flipped in this case. If d is positive, the function shifts right d units. So if d is positive, I might just add, so for example, let's say, we saw one up earlier there that was to the right, but let's say you were graphing x minus 2 to the power of 4, then that would be our basic quartic function, but shifted right, and it would start at 2, 0. So something like that. So you feel free to copy that on to your notes if you need to. But that's what it would mean. If d is positive, we're subtracting a positive number, and the graph shifts right. If the value of d is negative, meaning you're subtracting a negative number or you're adding, it shifts left d units. So I'm just going to put what that might look like in equation. So it's not, if maybe you're graphing, I don't know, x plus 1 cubed. That would be what it looks like when d is negative, and that would be a shift to the left. So those are the translations that you should be hopefully comfortable with after coming out of your grade 11 course. Let's continue. Group number 3. All right, so we're going to be transforming some cubic functions here. You know the drill. Pause the video, give it a go, unpause when you're ready. Now I'll just assume you've done that. Here's our third set. Basic cubic function. And when we multiply that base function by 2, you can see what we have is it's like a stretched out version. It's like that cubic function has been pulled and stretched upwards. Whereas 0.5x cubed, now the red value is the original. Those values are more squashed towards the x-axis. So what you might have for, I might just exaggerate things just for the sake of this note. So base function x cubed, x squared, things were stretched vertically. So, not to scale, but something like that. And then 0.5 x cubed, something like that's kind of squashed down. And the effect of multiplying by some a in front of the function. Now, right now, I'm just focusing on if a is positive. So I've included in this description here. So when you have a value of a that's not 1, the function is going to be its vertical stretch. I might even say into, I mentioned this later, but I'll say this now, or compression. It's a vertical stretch or compression by a factor of a. So if a is 2, it's going to be a stretch. If a is 0.5, a compression. So anything above 1 is going to stretch the function vertically, and anything between 0 and 1 is going to compress it. Now, I did put absolute value signs around in that definition there just to cover our bases after we allow a to be negative. But yeah, essentially, guys, if the size of the number is bigger than 1, it's going to be a vertical stretch. If the size of the number a is between 0 and 1, it will be a vertical compression. Now, those three transformations are you kind of touch on in your grade 10 course. This next one is not necessarily part of the grade 10 course and might have been new for you last year. So these equations look a little bit different. This time, instead of multiplying the function, the base function by something, I'm only multiplying the x by something. So let's have a look at what these guys look like. All right, so x to the power of 4. What effect does multiplying the x directly by 2 have? So you might hypothesize or remember from last year, it's going to be a horizontal stretch or compression, but which one? Let's have a look. And what's interesting is that, when you multiply the x directly by a number bigger than 1, it actually gives you a horizontal compression and not a stretch. And you can see that we have our red function as the original, and this blue function has been compressed towards the y-axis. And if we multiply the x by a number between 0 and 1, you can see that it's actually stretched out horizontally. So let's get those down. Get my pen tool back here. All right, basic quartic function, something like so. All right, now I might just exaggerate here. So what we saw in this graph was that the graph was compressed. It was kind of compressed in towards the y-axis. And here, 0.5, the graph was very stretched out. So I'm exaggerating here just for the sake of our note. Everything was kind of stretched out. And the effect of k, so multiplying just the x by a constant, it gives you either a horizontal stretch, and I'm just going to say to possibly just or compression. I know I cover both bases in there, but let me just add this in. And it's a horizontal stretch or compression by a factor of 1 over k. So we saw that in the second guy, by multiplying the x by 2, k was equal to 2, the graph was actually compressed by a half, 1 over that. And then here, when k was equal to 0.5, the graph was stretched by 1 over 0.5, which is equal to 2. So the rule works. The stretch or compression factor, horizontal, is 1 over k. That's something you guys developed and learned in your grade 11 course. Now, if the size of k, and again, I'm putting these in absolute value brackets to allow us to let k be negative in the future. But yeah, if the size is bigger than 1, it's going to be a compression. If the size of k is between 0 and 1, it's going to be a horizontal stretch. And again, this is all ideally review of last year. But last year, you didn't transform the quartic function or the quintic function, let's say. All right, one more for us to do. And I have these 3 loaded up in Desmos. Again, pause the video, give these a try, unpause when you're ready. But I might play around with this one a little bit more. So here we go. Basic cubic function. Now, when we multiply that basic cubic function by a negative 1, what we get is the graph has just flipped vertically. So this is consistent with what you learned in grade 10. Let's say you had the basic parabola x squared and then minus x squared. It just shifts it, reflects it vertically. It reflects it in the x-axis. That's the effect of multiplying by that negative. Now, what about when we multiply the x by a negative instead of having a negative out front. Now you might say, Mr. Smith, this is the exact same transformation, but actually here what's happened is we've got a horizontal reflection. The graph has been reflected across the y-axis, and I can show you guys an example of that. Let me just clear off things here. So let's look at an exponential function that you might have seen last year. There's 2 to the power x. I'm going to make 2 more graphs here. Watch what happens when I multiply that by multiply the entire function by -1. You can see that the graph has been reflected vertically in the x-axis, whereas if I multiply just the x by -1, then the function is reflected horizontally. So that should be familiar with you guys from last year. The thing is with the cubic function, because of its point symmetry and it being an odd function, if you reflect the cubic function vertically in the x-axis or reflect it horizontally in the y-axis, you wind up with the same graph due to symmetry. But as we saw with this exponential function, that's not the case. But yeah, we're looking at power functions today. So yeah, so I just used the cubic one as an example. Let's get this summarized and keep moving forward. So x cubed gave us our basic cubic function. Minus x cubed reflected things vertically. What was negative became positive, something like that. And we did end up getting the same graph. For the last one, but just summarizing these things, if a is less than 0, like this one, the function is reflected in the x-axis, so vertically. And if k is less than 0, the parameter multiplying the x, then the function is reflected in the y-axis. But again, because of the symmetry with this example here, guys, that's why those 2 final graphs look the same. But hopefully you were convinced with that power function, the exponential function example, that the vertical reflection and the horizontal reflection can look different. All right, let's continue. So we've got the 5 types of transformations. Let's just summarize these in a little visual. So not going to add too much detail here. So the effect of C is a vertical translation. I think we have enough space to add C is greater than 0, it's up. If C is less than 0, it's down. And then we looked at the effect of adding or subtracting a number off the x was a horizontal translation. And if we are subtracting a positive number, it translates right. And if you're subtracting, let's have that mixed up. I said positive and wrote less than 0. If you're subtracting a positive, shifts it to the right. If you're subtracting a negative, shifts it to the left. All right, now let's look at the value of A. I can give you a vertical stretch. If the size of A is bigger than 1, so something like 2 or -3 or 1.5, if it's bigger than 1, it's going to be a stretch. Or it could be a vertical compression. If the size of A is between 0 and 1, just kind of 3 points here. And then it could also give you a reflection in the x-axis. and that's if the A value is negative. And then finally, summarize for K. So what could this tell you? You get a, I'll just erase that. Horizontal, I was going to write vertical. Horizontal stretch or compression. But what we reviewed was if the value of K, the size of the number K, is bigger than 1, it actually gives you a compression. And that's if the size of K is greater than 1. It gave you a stretch if the size of K is between 0 and 1. And then we saw that you could get a reflection in the y-axis if K is less than 0. So a nice little summary of the transformations, and none of this should ideally be new to you. It's just in today's lesson, we're transforming power functions. So like things that you didn't necessarily do in your grade 11 course. All right, guys, let's continue. We're going to do a few examples, talk about some transformations. All right, so in this example, we're going to sketch a transformation of the base cubic function y equals x cubed. We're going to describe all the different transformations that are being indicated in this equation, and we're going to sketch it. And just to give you an idea of where we're going, there are many ways to go about this. What we're going to do, don't want to spoil the answer there, but what we're going to do is we're going to take points on the base function and kind of transform them a little bit at a time. Just apply kind of a couple of transformations at a time to ultimately get to some points that will be on our transform function, and that will allow us to make a sketch. This is not the only way to sketch a transform function, but by creating a table like this, it can be very helpful. But yeah, let's state the parameters and describe the corresponding transformations. So what would be great is if you guys had a bit of a think, pause the video. I'll just put them in order they occur in the equation. For this particular transform function, what's A, what's K, what's D, what's C? And then as you're getting those parameters, think to yourself, okay, what transformations do those parameters imply? So pause the video and give that a try. And when you're ready, we'll list the parameters and we'll talk about their effects. All right, I'll assume you've given that a try. So for A, we look out in front of the transform function, so we can see A equals -3. So we'll get this in words in a second, but it's negative, so vertical reflection. And that number 3 is bigger than 1, which means it's going to be a vertical stretch. K, what is in front of the x? If you were to expand everything out in the middle here, the coefficient of the x is 2. K is equal to 2. Now, when I'm teaching this, I'll often just get my students to automatically say, okay, well, what's 1 over K? Be 1 over 2. Because you guys can see, okay, it's bigger than 1, which actually means a horizontal compression. D, the value of D here is -1. Why is it -1? Well, it's because in x minus D, if you do x subtract -1, you get x plus 1, which is what the equation says. This is actually kind of familiar to, you don't have to write this down, but in your grade 10 course, when you learned about the vertex form of a parabola, remember how we write it out this way? And the vertex we say was HK, kind of the same idea. In this case, D is -1. It's the opposite of +1. So that just clues us in, okay, that's going to be a shift to the left. And then finally, C on the end is +5. That's going to mean a vertical shift up by 5 units. So if we were to describe those in words, the base cubic function is stretched vertically by a factor of 3 and reflected in the x-axis. That takes care of A. It is compressed horizontally by a factor of 0.5. That's what we get from K. And then from D and C, the function is translated 5 units up and 1 unit left. And so we've described those corresponding transformations, but now we want to make a sketch of it. How can we make a sketch? So one way to do that is to think of points on the base function and how they transform. And we're going to apply 1 or 2 transformations at a time. So the one important thing that you guys need to know is that you apply the stretches, compressions, reflections first. That's a really important idea. It doesn't matter whether you do the vertical stretch first or the horizontal compression first or the flips. It doesn't matter. As long as you do all of these guys first and then do the translations, you will have an accurate graph. So what we're doing here is all we're doing now is applying that horizontal compression, right? That 2 in front of the x indicates it's going to be a horizontal compression. So what we're going to be doing is we're going to take the x values and to compress them by a factor of 1 over 2, we just multiply by 1 over 2, right? So we have -1, -8, -0.5, -1. We're just compressing the x values. 0, 0 stays there. 0.5, 1, and 1, 8. And I guess I can write our little rule down here. What we did was we multiply x by that compression factor of 1 over 2. All right, now we're going to apply the vertical stretch and reflection. We're going to take those points and we're going to scale them up by -3, which will reflect and stretch it vertically. So we're going to, because this affects the y values, we're going to multiply y by -3. So -1, this guy going to be stretched to +24, -0.5, +3, 0, 0, 0.53, and +1, -24. I made a mistake. That should be -3. Just as a side note, if a transform point gives you the original point again, we call that being invariant. So the point 0, 0 is invariant under any stretch, compression, or reflection. All right, so now that we've stretched, we've compressed, we've reflected horizontally and vertically, we're now ready to translate. We're going to do both translations at once. So we're going to, because we're shifting things left, we're going to subtract 1 from x. That will move all the points left. And we're going to add 5 to y. That will shift all the points up 5 units. And so I'll just be careful with the mental math here. So that will be -2 and 29. That will be -1.5 and 8. -1.5. -0.5 and 2. And 0, I guess that would be -19. And what we're going to do next is we're going to, so those 5 points that kind of give the cubic function its kind of shape, right? We've now transformed those 5 points. If we plot them, we'll basically see the general shape of our transform function. So let's do that. So -229 somewhere up here. -1.58 somewhere here. -1.5 here. -0.52 somewhere here. And 0, -19 somewhere down here. And everything kind of checks out. You can see that it still has its kind of cubic function shape. It's just been stretched out and shifted a bit. And because of that leading coefficient that's negative, we get that end behavior that goes from quadrant 2 to quadrant 4. Now, I would like to just take a moment and stress, so you guys are at home. You guys have lots of technology available. And hypothetically, let's say this was a test question or something. You guys have these tools at home. You have access to graphing tools at home. There's no reason why you can't use a graphing program to check your answer afterwards, and to make sure you did things right. So I would strongly advise that. You know what? Maybe I can take my own advice here. Let's clear all these guys out, and let's give this guy a sketch here. Be careful to punch it in, right? So we have -3 and 2x. I don't know if it likes that square bracket. It doesn't. -3 and then 2 times x. 2 times x plus 1, and that's cubed, and then we add 5. Now if I make my scale look a bit more like the one in our note, from like what's one in our note? From -3 to 1 and -20 to 30. -3 to 1, -20 to 30. Okay. Now we have a really good comparison, and you can see that, the Desmos and our graph at home looks very similar. We did a good job. So I'd encourage you guys, as you're doing practice, as you're checking answers on something worth marks, just check with Desmos. It's not, if you do it first, try it on your own and then check. That's not cheating. That's smart. It's checking your work, right? Now, we don't want to rely on technology. You want to know how to do this by hand as well and know the underlying math. But using a technology to check is fantastic. All right, let's continue. A little note about even functions. So we all know that the quadratic functions all have a vertex. But quartic functions and even 6th degree, 8th degree functions will have a vertex as well. So, y equals x squared has its vertex at 0, 0. But if you think about the graph of y equals x to the power 4, it's kind of just like a flattened out version of y equals x squared. And y equals x cubed, this will be the last one I draw. You can see a bit more accurate graph, like maybe on Desmos or something. But it's like even flatter. But they all have something in common. They all have a absolute minimum, i.e. a vertex at 0, 0, right? This is true for all even even power functions, x squared, x4, x6, x to the power of 8. And if you translate them, so if you have a shift to the right, if you have a shift and a horizontal shift and a vertical shift, then that vertex will go from 0, 0 to whatever the shift indicates. And so that means if the vertex was at 0, 0, it's going to go to a new point, D, C. And the axis of symmetry will always be x equals d. However, that graph is shifted. And again, this is true, guys, for all even power functions, squared to the power 4, to the power 6, power 8, etc. As you can see from those images I put, if a is greater than 0, the graph will open upward. The vertex is the minimum point on the graph, and C has minimum value. The range of the function is always going to be y is a real number such that y is greater than or equal to C. So all this is saying is that the graph opens upwards. There's going to be a minimum value where the graph is always above. And then conversely, if a is negative, then the graph is reflected and opens downwards. The vertex will be a highest point or a maximum. And the range will then be y is a real number such that y is, so if you have a maximum, y is below that maximum point. So this is true about all even power functions in the transformations. All right, let's continue. So we're going to do two more. We're going to, we have in these questions, what we have is a base function, and then not exactly the equation, but the transformed function just in function notation. So what we're going to do for each one is we're going to pick off the parameters and describe the transformations, and then we're going to state the domain and range for each guy, maybe even thinking about what a rough sketch might look like. For each one that are even, we'll state the vertex and the equation of the axis of symmetry. So let's start. So if you want to pause the video and try all those on your own, that'd be fantastic. But yeah, let's chat about it. So right away we can see this is an even power, a quartic function. So we know it's an even function, and we know there's going to be a vertex. So and an axis of symmetry. So let's do the transformations first. I have them listed here. So it's stretched vertically by a factor of 2. That's because a is equal to 2. We look out front of the whole function, and we can see that a is equal to 2. K is equal to a third, which means 1 over k, the reciprocal, is equal to 3. So that's why the function is stretched horizontally by a factor of 3. The value of d is equal to 5. So that's where it's shifted right. And c is equal to 0. So you'll notice there's no vertical translation. Off to the side here, this question did not ask for a sketch, but I'm going to do a rough sketch, right? So we have I'm just going to draw like a dashed line. We have our basic quartic function. And I might switch to a different color here. And then it's stretched vertically by a factor of 2. Oh, orange is a bad choice. It's hard to keep track. Okay, so it's stretched vertically by a factor of 2. So the graph looks something like that now. Excuse me. And then the graph is stretched horizontally by a factor of 3. So it might look something now like this. And then finally, the function is translated 5 units to the right. So I'll get one final color here. The question didn't ask us to make a sketch, but maybe it's just helpful for learning purposes. And so if you translate that, you give it a final function. It looks something like this. And the vertex is going to, well, it was at 0, 0, and now it's going to be at 5, 0. And because it was shifted right 5 units, the line of symmetry, the axis of symmetry, is going to be at x equals 5. So let's just wrap this up. I'm in green, so let's just stick with green. So the domain. So we know for any polynomial function, the domain, x can be any real number. I'm going to use our interval notation for that. Maybe for the next one, I'll use set notation just to mix things up. For the range, so you guys can see the vertex is at 0, 5, 0, and it opens up. So the range is always going to be, if it opens upwards, it's going to include that lowest value, which is 0, and then it shoots off upwards to infinity. The vertex, we visualized the vertex here is 5, 0. And the axis of symmetry is the line x equals 5. Now, the one thing we didn't do is we didn't write the corresponding equation. So what would this kind of general transform function look like if you actually plug that stuff into the base function? Well, it looked like this. So we have y equals, so the value out front is 2. Okay, and our function f of x is x to the power of 4. So I'm just going to put some big square brackets here to the power of 4. And then inside there, it's not x to the power of 4. It'll be 1/3 x minus 5 to the power of 4. 1/3 x minus 5 to the power of 4. So that's what the equation of that corresponding function would look like. A is 2. K is a third, D is 5, C is 0. We're going to try that with one more. So can you guys kind of repeat the drill with this one, a quintic function? I'll let you guys give it a go, and just pause the video, unpause when you're ready. Might be a surprise in this one, but let's just see how you do. And yeah, just give it the old college try, guys. I won't leave you hanging. So I'm going to assume if you've wanted to, you've paused the video, you've given this a try. So there's actually a twist to this one. This notation here does not quite look like, if I can go back to our summary, doesn't quite look like this. If you guys look at K times X minus D, that's factored, right? The one we are working with right now, inside that argument, we have of the function, we have minus 2x plus 6. We actually need to rewrite it. And this should be familiar to you guys from your grade 11 course. But we actually need to write this as minus 2 all factored x. And when we take out minus 2 from 6, we get minus 3. So now it's in the form that we're familiar with to pick off all the transformations. So now we can do it. A is a quarter, vertical compression. K is equal to negative 2. So 1 over K is equal to negative 1 over 2. So it's going to be a horizontal compression and a horizontal reflection. And then we can see that D is equal to 3 and C is equal to 4. So shifting right 3 and up 4. Describing those transformations, I overlapped a little bit there, that's okay. Our base quintic function is compressed vertically by a factor of 1 over 4, compressed horizontally by a factor of 1 over 2, and then reflected in the y-axis. And then for the translations, 3 units right, 4 units up. Again, guys, you can compress vertically and then horizontally, or you can do the horizontal first and the vertical first. None of those, the order matters. As long as you're doing stretches, compressions, and reflections before translations, you'll be okay. And the translations can be done in any order. You can go up and then right, or right then and up. It's the same thing. But again, stretches, compressions, reflections first. Okay. What is the corresponding equation? So the equation would be, so it's a quintic equation. The A value is 1 over 4. And then our brackets to the power 5. We are adding 4 on the end. And then what's on the inside? We have K is minus 2, and then D is 3x minus 3. There's the corresponding equation. And now, guys, this is an odd function, right? The quintic function, y equals x to the power 5. It doesn't have a vertex, and there's no transformation we could do or combination of transformations that would make it have a vertex. So for this one, we don't have to, we're actually done. We just can state the domain and range. And as we've learned earlier, the domain and range for any odd degree polynomial function is the same. Now I'm just going to mix it up, but I'm going to use set notation here. The domain is x can be any real number, and the range, y can be any real number. Yeah, we don't have to do the axis symmetry either. And you know what, guys? Since we're here, I know the question did not ask for a graph, but we can just draw a quick one. You can follow along if you'd like. No pressure though. Yeah, why not? So let's do one transformation at a time. So the base quintic function is compressed vertically by a factor of 4. So we're making a rough sketch here. And orange is a bad choice. There it is. There it is. So compressed. So everything gets squished down towards the x-axis. And then compressed horizontally by a factor of a half. I'll do that next. I'll use this color. So I don't know, maybe something compressed horizontally, something like that. and then reflected in the y-axis. So let's get a new color. Running out of colors, let's use purple. And then it would be reflected. Again, this is just a rough sketch of what it might look like. And then finally, we translate that 3 units right and 4 units up. 3 units right, 4 units up. I'll just use red for the finished product. So 0, 0 would go 3 right and 4 up. So somewhere up here. And then our behavior is, something like this. Just a rough sketch. And you can see from our rough sketch that the domain is going to be x can be any real number and the range y can be any real number. Again, same for any polynomial function with an odd degree. All right, now just to maybe reinforce, if I really want a detailed sketch, then a proceeding like this question would be helpful. Find the parameters and describe the transformations, and then apply them. In our example here, we did the horizontal compression first, and then we did the vertical stretch and reflection second, and then we did the translations. So deal with kind of like a possible algorithm for doing this is, deal with the k value first, and then the a value second, and then the c and d values lastly. Now, if you have some kind of method for transforming functions that worked for you in grade 11, by all means, continue to do so. This can just be one helpful way to sketch a transform function. All right, guys, I believe that's it. It is. What's up next? So we've kind of done our introduction to polynomial functions. In the last 2 lessons of this unit, we switch gears a little bit and we revisit rates of change, and we talk about 2 specific types of rates of change: average rates of change and instantaneous rates of change. And this is kind of the point in time in the course where we introduce these ideas, kind of getting you ready for calculus in a sense. For today's lesson, I've got some suggested practice for you guys from the McGraw-Hill Ryerson textbook. But yeah, guys, until I see you in the next lesson, hope you're doing well. Good luck with your work. Please reach out if you need anything. And yeah, have a good day, guys.